Hello, this is Charlie and Jalen, and for our fluid dynamics project, we're looking at hydrodynamic levitation. Um, it's a process where a object is suspended in a position by a fluid. So there's a streamline of water going up into the air, and a ball is going to be suspended in the air with centrifugal forces.
The fluid is able to counteract the force of gravity put in the object, causing it to take on the appearance of it being suspended in midair. The way it works is, as the water shoots up, it rotates one side of the ball, and the rotation of the ball counteracts the force of the water being pushed on the ball, and pushes the force of the ball pushes back into the water, keeping it in one position.
The two equations we used for this is the Bernoulli's principle and the Magnus equation. The Bernoulli's principle was used to find the velocity of the liquid as it was going into contact with the ball. The Magnus equation was used to find the force vector that was pushing the ball back into the stream of water. For our experiment, we used two planks of wood. We glued them together and drilled a hole at the top. We did this so when the nozzle is inserted into it, it is flush with the surface of the plank of wood, making the calculations of the initial elevation easier. And we also drew a line along the ridge of this ping pong ball, so when it rotates, we're able to easily count how many rotations it undergoes every second. So we can use it. You can use that for our calculations. To find initial and final elevations, we used this level rod right here, and to make sure it was level, we used this level here. So what we did was we attached it like this. We made sure it was level, and then after it was level, we taped it to a wall, so we didn't have to hold it throughout the entire experiment.
This is a picture of our setup. We used two concrete cylinders to hold down a plank of wood to make sure that the nozzle was level. We used the level rod behind this to find initial and final heights. The following video shows how we were able to get angular velocity of the ping pong ball. We counted how many times the ball rotated in air per second to be able to find RPMs.
During the experiment, one of our main goals was to find the velocity of the water shooting out of the nozzle. And in order to do that, we first had to find the volumetric flow rate of the water coming out of the nozzle. The way that we were able to find the volumetric flow rate was we had a 1 gallon bucket, and with the same velocity that the water was coming out of the nozzle, we took it and we timed how long it would take to fill up the bucket. This is a 1 gallon bucket. So once we got the time, we took that and we converted it from 1 gallon per how many seconds it took to fill this up, and we converted it to meters cubed per second to get the volumetric flow rate.
This video demonstrates how we were able to find the volumetric flow rate from the nozzle. We used a 1 gallon bucket and timed how long it took for it to fill up, and we converted that to meters cubed per second to find the volumetric flow rate.
So as you can see in this picture right here, we have all of our givens: the nozzle diameter, bucket height, ball diameter, and ball weight. We use all of these in these equations below. To find the height of the water, we first recorded the initial height of the datum on the level rod, and we recorded how high the water was able to reach, and we subtracted that to find the total height of the water. After that, we used the bucket diameter, the bucket height to find the volumetric flow rate, which is where we timed how long it took to fill the bucket to 1 gallon, converted it to meters cubed per second to give us the volumetric flow rate. To find the velocity of the water at point 1, which is our datum, we took the volumetric flow rate equation, which is the average velocity divided by the cross-sectional area of the nozzle. We moved it so that we can find velocity, and we plugged in the volumetric flow rate in the cross-sectional area of the nozzle to get 5.48 meters per second. To find the velocity of the water at point 2, we used Bernoulli's equation, and we were able to cross out the pressure at point 1 and the pressure at point 2 because they're both atmospheric, as well as the height at point 1 because it is 0 because it's our datum. And that left us with velocity 1 squared divided by 2 equal to velocity 2 squared divided by 2 plus gravity times height at point 2. And we moved this equation around to give us the velocity at point 2, which then came out to 1.72 meters per second. And then finally, to find the Magnus force of rotation on the ball, we use the Magnus equation, which is density times 4 pi squared times the radius squared times the rotations per second of the ball times velocity at point 2. S is the rotations per second, which we converted to 1.34 meters per second. And once we plugged all those values in, we got a value of 34.4 newtons or 7.73 pound force.